Hello, everybody. So then the previous video, I went over the reason why we talk about similarity, because we're hoping that a matrix is similar to a diagonal matrix, because then taking powers of that matrix is really easy. But I only gave you one way to figure out if a matrix is diagonalizable. It has to have n linearly independent eigenvectors. But I can go a little bit deeper than that. That's called the diagonalization theorem. Now, this theorem is one of those results that is not super intense, but symbolically is pretty awful. So then if you just want the result, I'll tell you when you can stop watching. If you want to see the reason why, we just continue. Okay, so the only thing you need to know is the result. The proof, again, you don't get anything out of the proof other than getting a better feeling for how to argue other statements later in life. So to do so, though, I need a theorem, though, that we could prove. We have all the tools, but to prove this result would require me to prove some other sub-results first. And I just don't care about any of the sub-results, and neither would you. So because of that, this is one of those, we're just gonna mention it. I'm not even gonna give you a proof. I'm just gonna go, it's true. If you wanna look in the book actually gives you the proof. But even then, there's a number of places where it just says this is obviously true, and it's not obvious. It's something you'd have to prove to explain. So it winds up being that if you give me any eigenvalue, for any eigenvalue, its geometric multiplicity never exceeds its algebraic multiplicity. That is true for every single eigenvalue. Again, this is not beyond the course. You could prove this with what we have. That's just not worth our time, because I have to prove other results that we just completely don't need. So we're just going to accept it. That then brings up the diagonalization theorem, the big result, the thing that tells us when a matrix is diagonalizable or not. So let's say you have A is an n by n matrix, and it has k distinct eigenvalues, lambda 1, lambda 2 up to lambda k. Now, the algebraic multiplicity here would be bigger than 1 for a bunch of these probably, because the algebraic multiplicity of each of these, when you add those together, has to equal the degree of the characteristic polynomial, which would be n. So the following statements are all equivalent to each other. The matrix is diagonalizable. The particular matrix has n linearly independent eigenvectors. And then the next one, the one we actually use a lot, is that if you take the union of the bases of the eigenspaces, that has to contain n vectors. That's how we use it all the time. If the union of the bases of the eigenspaces contains n vectors, then the matrix A is diagonalizable. The matrix P is just the matrix of all those eigenvectors. And the diagonal matrix is the diagonal matrix whose entries are the eigenvalues in the corresponding seam spots. So the first eigenvector goes with the first eigenvalue and so on. Also, though, which is really nice, is that the algebraic multiplicity has to equal the geometric multiplicity for each and every eigenvalue. So if you ever have a matrix whose algebraic multiplicity exceeds its geometric multiplicity, instantly that matrix is not diagonalizable. You actually don't have to keep going. So this is it. If you want to, you do not need to watch the rest of the video. This is the big theorem. You'll hear me mention this a few times. At the end of the video, I do one quick example to show you that a certain matrix is not diagonalizable. Remember, if it is diagonalizable, the matrix P is the matrix of eigenvectors, and the diagonal matrix is a diagonal matrix whose entries on the main diagonal are the eigenvalues in the same order of the eigenvectors in the matrix P. Okay, you've been warned. Let's go on. So let's prove it. I'm going to prove then that if A has n linearly independent eigenvectors, then the union of the bases of the eigenspace actually contains n vectors also. Why? It's because you're actually drawing from the same set. So what I want to do is this. Let's say B sub I is going to be a set of vectors. They're going to be a basis of E sub lambda I. So that's the eigenspace going for the ith eigenvalue. Let n sub I be the number of vectors among the n vectors that are in this eigenspace. Well, the original vectors, the original n vectors are linearly independent. That means that these n sub I vectors are also linearly independent. But that would then mean that the basis b sub I has to contain at least n sub I vectors, because the basis, you remember, is at least the dimension of the space. It's the maximum number of linearly independent vectors. So if you already have n sub I vectors that are independent in that eigenspace, then the basis has to have that same number or more. Therefore, the union of all the vectors in this basis must contain at least n sub 1, n sub 2, n sub k, which is just n vectors. So the union of these vectors in the end, the union of all these vectors has to contain at least n vectors. But we know, though, from a previous theorem that the union of these vectors are already independent. The union of all the vectors in these separate bases would be linearly independent from a theorem I gave you for a previous class. So that means that the union of them can't be more than n vectors, because the maximum number of linearly independent vectors in Rn is n. So then it can't be more than n, it can't be less than n, it must be n. That's it. So that then shows you then among these n linearly independent eigenvectors, actually they form the basis for the different eigenspaces. You just have to figure out which eigenvector goes with which eigenspace. Okay, so that's that one. Let's now go to the next one. So the union, let's suppose that the union of the bases of the eigenspaces contains n vectors. Then I'll show you that the algebraic multiplicity of each eigenvalue, it has to equal the geometric multiplicity. This is just a matter of counting things correctly. So let's suppose d sub I and m sub I is the geometric and algebraic multiplicity of the eigenvalue lambda sub I, respectively. All right, well then, that means then from a theorem I've already mentioned that we're not proving that for every I, the geometric multiplicity is no more than the algebraic multiplicity. So d sub I is no more than m sub I. Well, but by assumption, though, that when you take the number of vectors in the different eigenspaces and put them together, you get n vectors. Well, the number of vectors in the first eigenspace is d1. The number of vectors in the basis for the next eigenspace is d2. So then if you take d1 plus d2 plus d3 up to dk, that's got to be n. But we also know, though, that the sum of the algebraic multiplicities of these eigenvalues has to equal the degree of the characteristic polynomial. But that's n. So m1 plus m2 plus mk has to equal n also. So these two sums are equal to each other. So d1 plus d2 up to dk equals the sum of m1 plus m2 plus mk. What I want you to do now is subtract things. So I want to subtract d1 on both sides, d2 on both sides, and so on. You then get, and by collecting terms, you get m1 minus d1 plus m2 minus d2 plus, and that keeps going until you get to mk minus dk. That's got to equal 0. But every single thing in those parentheses is non-negative, because m1 is at least as big as d1. M2 is at least as big as D2, and so on. So I'm adding a bunch of non-negative things, but the sum is 0. The only way that's possible is you're adding up a bunch of zeros. So then everything in the parentheses are 0. But then that means then in every parenthesis, you would get that, for example, M1 would have to equal D1 because that difference is 0. M2 would have to equal D2 because that difference is 0, and so on. So that shows then that the geometric multiplicity is equal to the algebraic multiplicity in for every single eigenvalue. All right, good. So that's that one. Last one. So let's prove that the algebraic multiplicity is equal to its geometric multiplicity. No, sorry, if that's true, if the algebraic multiplicity is equal to the geometric multiplicity, that means instantly that we have to have n linearly independent eigenvectors. It's really easy to prove. So then let's say then d1, d2, so on is the geometric multiplicities of the different eigenspaces. M1, M2, so on is the algebraic multiplicities of those spaces, of those different eigenvalues. We already have then that d1 plus d2 up to dk that has to equal M1 plus M2 up to MK, because we're assuming the algebraic multiplicity equals the geometric multiplicity. But we know that the sum of the algebraic multiplicities has to equal n. So the sum of the dimensions of the eigenspaces has to equal n. Just take all those eigenvectors and put them together. They have to be linearly independent. And there's n of them. So there has to be n linearly independent eigenvectors. And that's the proof. It's really easy. It's really easy. Just arguing the same things over and again. You might want to have a way to use this quickly. It's actually really useful to show that something's not similar to a diagonal matrix. Because if any of those statements are false, then it's just not similar to a diagonal matrix. The only time we ever use it to actually find the similarity between the matrix and the diagonal matrix is the original theorem. You just take the vectors in the basis for each eigenspace. If the matrix is diagonalizable, when you put all those vectors together, you have to have n vectors for an n by n matrix. Those vectors put together will make the matrix P. And the diagonal matrix is just the diagonal matrix with the eigenvalues on the main diagonal. So look at this matrix. You saw this one before. I went back then, I showed you how to find the eigenvalues and I found the corresponding eigenspaces. Let's do that again. So here's me finding the characteristic polynomial. That then gives you that characteristic polynomial. From this, you can then tell that the eigenvalues are 0 and 1. 0 has an algebraic multiplicity of 2. 1 has an algebraic multiplicity of 1. To find a basis for the eigenspace corresponding to the eigenvalue of 0, I need to find a basis for the matrix A minus 0 times I. Here's me doing that work. Notice then the basis has only one eigenvector. There's only one vector. So the geometrical multiplicity of this particular eigenvalue is only 1. Its algebraic multiplicity is 2. So if I want, I could stop it. This matrix is not diagonalizable because the geometric multiplicity does not equal the algebraic multiplicity for the eigenvalue of 0. So this matrix cannot be diagonalizable. That's unfortunate. That means taking this matrix to high powers may not be fun. We would need more linear algebra to figure out what to do with it. Now, you could also look at the other eigenvalue for fun. The other eigenvalue has only an algebraic multiplicity of 1. Instantly, though, the algebraic multiplicity being 1, we know the geometrical multiplicity can't be more than 1, but for every eigenvalue, the geometric multiplicity is always at least 1. So without doing the work, although I did it for you, for the eigenvalue of 1, since the algebraic multiplicity is 1, it has to instantly equal the geometric multiplicity 2. Notice all you need to show is that in at least one of the eigenvalues, the algebraic multiplicity just doesn't equal the geometric multiplicity. That will then show you that the matrix is then not diagonalizable. If in every eigenvalue they are equal, then by putting all the eigenvectors together, that's the matrix P that gives you the similarity. And the matrix D, the diagonal matrix, is just a diagonal matrix on the main diagonal is the eigenvalues. That's really neat. And I believe that's enough for that video.